Thank you, Carlo. Okay, so now we are going to talk about processing text data. So there is a point in common with the audio is that we are talking about processing sequences with neural networks. So I will first introduce what is special about text data with respect to audio or images. And then I will present four types of techniques to process text. So for the embeddings, which is present in all the processing, so we'll see what it is. Then I will show an example of classification of text, an example of language models, and finally an example of sequence-to-sequence models that are used to do, for example, translation. So first, what is special about text? So it's that we have a variable length sequences of tokens. So what we call by tokens is a symbol. So yeah, languages are big sequences of symbols. And in the world of neural networks, you can decide to model this symbol at several levels. So these symbols can be characters, words, and punctuation marks, or even multi-words, groups of words or sub-words. It depends on the task, what is the most relevant. And also, when we talk about text, the scope can be different. So we can process a word or a sentence or paragraph, an article, a book. It really depends. To illustrate the token thing, I will show how we can tokenize, that is to say, to split this string into some symbols differently. So he did a 360, so it can be tokenized like this with word and punctuations, but we can decide also to do special things for digits if we want a model that will be good at processing digits, for example, or we can decide to tokenize in character like this. And also, it's the text has some underlying structure, like we can show with text structure. But in practice, with neural networks, it's not very successful nowadays. The approaches that try to first find the structure and then exploit this structure, because if you make an error when detecting the structure of the text, then the rest will fail. And actually, the structure is very complex and even analytic. It's not well defined in the sense that if you ask several people what is the structure of a given text, you might have different answers. Not in this simple case, but in more complicated case. So, yeah, in my presentation, in all the approaches, I will treat the text as a flat sequence of symbols. Then the neural networks, they take inputs, which are text, and they output something, and the output will depend on the application that you want to do. So for example, if you want to do classification, the output will be a single class or probabilities over classes. So application are sentiment analysis and topic classification. So for example, there is already a sentiment classifier in the language. You give a text and it just output a class or probability of classes. And the regression problem is we have also this sequence of symbols and you want to output a number. So for example, sentiment analysis is again an application where you may want to score the sentence with respect to its probability of being positive. And then there are a group of tasks which are called transduction, where the output is also a sequence. So I distinguish two cases. One case is where these sequences are the same length as the input sequence. So for example, is the part of speech tagging, where you have a sequence of words and you want to tag what is the role, the grammatical role of these words within the sentence. There is also named entity recognition. So you are given a sentence and you want to detect like this, where are the person, where are the cities, the dates, and all kinds of entity types. There are also language model, which I will illustrate later, when you want to predict the probability of a sequence, and usually it's done by predicting the probability of each symbol given what comes before. And another application is to question answering by pointing something in the text. So actually you're given a text, which is a list of symbols. You are given a question. So for example, here we ask, where is born Michael Jackson? And actually the model is going to give the position, so in terms of characters. So either you can modelize it with words or character, but This model works by detecting first the start position and then the end position. So you've got the same number of input and outputs in the network. And here, for example, it's outputting Gary, and you can watch the position of Gary in the original string. Okay, and if I ask when he's born, then it will focus on another word with another span. Okay, and there are also a bunch of a group of applications where the output sequence has a different length than the input sequence. So, for example, machine translations, translating a language to another, but it can be also more general, like translating natural text to a program, for example, writing a program from natural text. All these kind of applications, you don't know in advance the length of your output sequence. Also for text summarization, you are given a big text and you want to summarize it. Or question answering, the same application like before, but by generating a text, like here in find textual answer, it will always give a span which comes from the input, but maybe you want to generate the output. Okay, and conversational modeling also. So a few words about processing text. So there are basically 3 steps that are done. So I already talked about the tokenization, like transforming a string to a list of symbols. Then you may want also to clean the text, like to remove the stop words, or to lowercase, to do stemming also. Stemming is it's a rule-based approximation of lemmatization, so it's about removing the plural forms and the infinitive forms of the verbs. But stemming, is only rule-based, so it can create words that do not exist, like the R here, which come from this. Normally, lemmatization would be like the infinitive verb for this one, but stemming is only based on rules. Okay, and then once we have the symbols, which are string, we have to convert them to indices, because it will be too cumbersome to handle strings in neural networks. So first, we want to convert them to indices, and then later on to vectors, so numerical vector, and then it's usual neural networks. So there are 2 ways of, so there are already 2 net encoders to process text in the language. There is one which will output so net encoder characters, which will output indices corresponding to some characters. So if I put 3 characters, it will output 3 indices. And there are a lot of options where you can specify your set of characters, including special characters like start of string and end of string. And the other useful one is net encoder tokens, which will produce words. So for example, if I give it two words like this, I will have 2 indices at the end. Okay, and then once we have these indices, usually we map them to some vectors which can be learned. Sorry. Yeah, so this is my next section. We call this embedding. It's the process of mapping a symbol to a vector, which is supposedly semantically meaningful. So the most basic embedding is called one-hot encoding, and in the language it's called unit vector layer. So yeah, it's just a layer that will output a vector with the same size as the number of tokens it has in the lexicon, and with one activated. Like for example, if we put the unit vector on characters on the word yellow, so it will produce four numbers, yeah, and here it's only activated at the index which correspond to the letter H, E, L, L, O. Yes, sorry, there are 5 characters and 2 times L that we see here. Okay, so this representation is not learned basically, and but we can also what is more typical actually is to map all the indices to a vector of arbitrary size. So this is done with the embedding layer. And it will map, so for example, if I do the same with the word hello, but I want a dimension of 30, whereas before I was stuck with the number of characters in my dictionary of characters. So here I have, for every row correspond to a character, and I have 30-dimensional vectors, which are random, but which can be learned later on. And actually, if you chain a unit vector layer with a linear layer, is the same as doing an embedding. Like I show here, I took the weights learn and put them in an embedding, and I got twice the same results here. Okay, so this is the general principle of embeddings, and they can be applied to the tokens, so to characters, to subwords, words, or multi-words. And actually, there were historically these embeddings were the first breakthrough in neural networks for natural language processing. So there were Word2Vec and Glove, which are gave some performance improvement in all the models. So they were trained basically by scraping huge database of text and having some criterion based on the co-recurrence of words. For example, they were learning representation that are good at predicting the next word or the surrounding words, or by matrix factorization techniques on the co-occurrence matrices of words. They come up with some meaningful representation, semantic vectors for the words. So here we see the dictionary. So there are 400,000 words in this model. And to illustrate how semantic they are, so here I took 3 lists of words which are in different categories: animals, colors, and fruit. And if I plot them using a feature space plot, then I see the 3 groups are well distinct. So it means it encodes the meaning. These vectors encode the meaning of the words, and so they are very good, for example, to solve the ambiguity, the synonymy stuff. Yeah, for example, you have 2 words that means the same thing. If you assign them a random well, the distance will be close with this, and your neural networks won't have then, if you feed them with these word embeddings, to learn which word are synonym. You already have it as an input. Okay, and also there are some interesting properties. For example, in this plot, you can see that going from the male gender, like going from uncle to aunt, or from king to queen, or to prince to princess, is like it's always the same translation vectors. So not only the distance are meaningful in this space, but also the linear transform means something. And so, for example, you can do some arithmetic operation. For example, king minus man plus woman equal to queen. This kind of things. So there is the something. So here, all these models are in the network repository that Carlo already advertised, and I think. And so you will see by domain with text, you will see that there is a lot of these embeddings, the Glove embeddings. Yes, and another one is this one, ConceptNet. This one has the particularity of working on phrases, that is to say, on group of words. So, for example, here I plot the nearest neighbors of live in peace, and actually I plot it here. And you see so that there is a cluster here of words which are rather positive expressions, and then you have also the antonymic, which are not so far away, which means that there is a component in this vector which knows that peace and war are close together in terms of topics. And it's also multilingual, like it contains some word. I would not pretend it can do translation, but here I do some arithmetic. Bonjour, which means hello in French, minus hello plus goodbye, and we see au revoir appearing, which means goodbye in French. Okay, more interestingly, because these word embeddings, they apply a vector to a word independently of what happens around this word. So actually they solve synonymy, but they do not solve the ambiguity of a word that can mean several stuff, and depending on the context, it can mean several stuff. So recently, Allen's Institute released some very interesting word embeddings, which are now in our repository, and which have two main good points, let's say. First, they are only based on character embeddings, like they don't have any, it's not based on a dictionary of words, because the problem with the token embeddings is that if you got a word that is new, that is not in the dictionary, then you can only assign some arbitrary vector to it, but you are not going to process it correctly. And so in these embeddings, they start from character embeddings, and so yeah, I will use this representation of neural networks in my presentation. So yeah, the sequences have to be read from top to bottom, and then each little square rectangle here is a vector, and the big boxes are the layers. Okay, and so what happens in this model is that you first convert characters to indices, then you feed of an embedding layer that assign small vectors to each characters, and after you've got layers of convolutions apply, and then a max pooling on these convolutions, and then it produces one vector for one word. And then this list of words is fed, goes into a recurrent neural networks that Carlo already introduced, that are very popular to process sequences. And this is the part that gives to these embeddings the fact of being context dependent, because the output after the recurrent layer of a word will depend on what comes before and what comes after. So yeah, this is the model in our repository. So yeah, this was a simplified sketch that I made, because actually concerning the convolution, this part are running several convolutions in parallel with several sizes of kernel. So it's like looking at 1 gram, 2 grams, 3 grams, etc. of characters. Then they combine everything. Then they have this skip connection, which is known as the highway network architecture. Then at this point here, they have an embedding that is not context dependent. So here each word was treated independently, and then it's fed to two levels of neural networks, and then it's producing not only one but three vectors. Actually, they released it like this. So this at this point where we are context independent, we can access this. So we have an embedding that is context independent, and then two embeddings that are context dependent and more or less higher level, like it's one layer of bidirectional RNN or two layers of bidirectional RNN. And so if you give it two words, you will have two vectors for each one of these ports, which are dimension 1024. And Allen's Institute recommend to use by default the averaging of these three embedding. So that's what I am doing here. I'm just taking the network, adding this threading layer, which is computing here the average of the three ports, and I'm connecting the three ports whose name I get using netform information to the threading layer, which is here, and then I have only one port output of size 1024. Okay, which I can see it if I give it. Okay, and now let's illustrate what the fact that these embeddings are context dependent. So here I give several sentences with starting with the word apple in different contexts. So sometimes it means the fruits, sometimes it means the company. Sorry, there was a problem with the presentation mode. Contextual embedding. Okay, I was here. It does not want to. Okay, so yeah, here it's a feature space plot. So with the embeddings, and we see that we clearly distinguish the three sentences that are talking about Apple, the company, and from the three sentences which are talking about Apple, the fruit. So with these embeddings, we are going to disambiguish the word Apple depending on the context. So now I am going to show with an example of text classification how to use this embedding for a real application. So I took sentimental analysis as an application. So we have a data set in our repository of data, which is about movie review. So you have sentences which are review about movies, and they are assigned positive or negative label depending on if they are negative or positive. So I tested 3 models. First, random embeddings. So I took the glove one, and when you call the model, you can specify that you want the uninitialized net. So you will only have the same architecture, which is only 1 layer in this case, but it will be uninitialized. So you have the same the same stuff, but weights will be random when you train with it. And I put it in a classical architecture, which I should present, by the way, of classification. So in classification, you have your embeddings of words, for example, and you can fit it either to a convolutional neural network, as illustrated here, or a recurrent neural network, something that will combine all the information in the sentence. Then you have to pool. It can be done with a max pooling, or in the case of neural networks, you can also decide to take only the last vector also. Yes, the recurrent can be bidirectional or not. And then once you have a vector, it's the classical approach. You feed it to a classifier, which can be only a linear layer and a softmax layer. Okay, so this is the architecture I did here with my embedding layer that is going to be randomly initialized. That's why it's red now. I feed it to a bidirectional neural network, some dropout to regularize, some linear layer, aggregation layer of max to do some global max pooling, then a linear layer and softmax. Okay, I'm not going to run the trainings here to be fast. I pre-computed them, so yeah, this one gives this one. After I do the same, exactly the same experience, but I take the real glove, not the uninitialized one. So you see here, it's not more red, the first embedding layer, so it means it's initialized. And I've got this results. Okay, I don't know if you noticed here, I had 26 validation error. Here I am 21, so I already improved. And if I take now the Elmo, so like I said, I illustrated before, I take the average of all the embeddings that the Elmo gives. As this one is computationally expensive to compute, what I recommend to do is to pre-compute, and Allen's Institute also recommend this, to pre-compute them on your dataset, and then to train your classifier that is on top, what is on top on it, as a separate stuff. So yeah, I won't run it also here because it's taking some times, but I can pre-compute my training data and my validation data, the outputs of the Elmo, and then the hat I'm going to put on the network is all the following. So the dropout, the linear, the pooling, and the classifier with the softmax. And now, yeah, when I train this, the results are much better. So yes, I sum up everything. Like, these are the 3 convergence curve. So this is the validation error rate. Going through the training, so we see that the random embeddings is performing worse, and Elmo is performing the best. And then we have also the chart of the 3 validation rates. So we clearly see that using pre-training embeddings helped, and this is the power of transfer learning. Okay. So language model, some generalities. So language model is about predicting the sequence of the next word given the beginning of the sentence. And typical uses are, for example, autocompletion, or they are also used to improve speech-to-text or image-to-text system as a post-processing. Like if your acoustic or optical model do some mistakes, then maybe knowing the language, you can correct them. It can be used also for data augmentation, like if you are able to generate text, maybe for some tasks, you are going to use this automatic generator to have more training data if you know how to label some data. And it can also be used for fun, like you can create pseudo words or stories or article out of nothing. So the architecture is the following. Actually, it's very similar to classification, but you are just going to classify given the history. So classical stuff is to do recurrent neural networks, then to take the last the last representation to predict the next word, basically. So we have in the net, we started to feed the net repository also with some models. So this one was learned on English, and yeah, I should specify. Oh, sorry. Yeah, so once you have this network, as the output encoder is the net decoder class, you will be able to call on it all the property of the net decoder class. So for example, if you want you can ask for the top probabilities. So here, for example, I gave WH as the beginning of the sentence, and I asking for the probability of the next letter, and we can see that there is I, E, Y, and I and O coming first, which give rise to all the why question, like what, where, why, while, or with, or whose, all this kind of stuff. I can, by default, if I ask, it will the output will output me the most probable one, and then I can ask for random sample also. Each time I call it, it will give me a random sample from this distribution. This is the distribution for the character that is estimated, and it will sample from this. And then from this model, we can sample as many characters as we want next, and it can be done efficiently during NetState Object. So NetState Object was introduced in the last version, and it's an object that stores a network and all its intermediate activation. Because when we are going to generate, so you are going to generate here, given the begin, the next characters, but then you are going to feed the input, and you want the next character. But instead of passing again the full sequence, you don't want to do this. So you want to store the internal state where you were at the last point. So this recurrent state, basically, to continue. So that's what is done in NetState Object. So what we want, for example, to do, typically we want to sample like this, and then if we add the A, it will give the next one, then I add the T. That's what we are going to do with this function here, generate random, which creates a NetState object with the network, and then it's going to nest it. So just to show what is doing nest list. So if you give it a list and the start and the length, no, sorry, something is wrong. No, there is no list, sorry, just the start and the length, and I have to put something real for the length. Yeah, so it will give you the start, then what you predict on the start, then it will apply a nested function of f. So if you do it repeatedly on your sequence, then you will generate all the characters, and you only have to do a string join after to get the results. And so I can generate a random sentence like this, which are more or less funny. Or if I want to generate out of nothing, I can generate a point, and then it will start a new sentence. So for data augmentation, it can be used. Or if I want to start with a given name, I can do this. Okay, I have a part to show how to train this kind of models yourself, but actually, as it is very similar than what, or maybe I can do it very quickly to introduce a notion that will be useful after. So yeah, you will take a text corpus, you will analyze, for example, the characters that you have in your corpus, define your network, and then to train it, we are going to use what we call teacher forcing. So I remind that the network has to predict the next characters, and teacher forcing consists in just ignoring what predicts the network. You just fill with the next target. So for example, you have the start of sequence, you have to predict the T. Whatever will predict the network, you copy the T as the next input of the network, and then it continues. So this is what we call teacher forcing. And in our framework, it can be implemented with the sequence rest and sequence most layer. So that's what we are going to see in this picture. So I take my input, I remove the last character and I give it to my networks that have to predict the next characters. And then if I give it also to a sequence rest layer, it will remove the first frame, the first symbol, sorry, and then I will have this shift like this and do a teacher forcing. So after I plug with my loss, which is a cross entropy, classical for classification. Yes, and then this is a function. Also, this is practical for text processing because normally the databases are huge. Here I'm showing how to use a data generator. That is to say, instead of passing to NetTrain a dataset that is already all computed, I pass it a function that generates my samples. So if, for example, I define a function that will go and get some substrings from my big text corpus of size between 5 and 30. This is purely arbitrary. And there is a batch size also, like if I say 8, it will output me 8 samples. So these are random crops, if we can say so, of my big corpus. And these are my training samples. Like this, I show to the network variable length sequences, etc., etc. So here again, I don't show the training, but it converges. And then I have to extract the net and the prediction part of the net, because I remember that the network was wrapped into another network like this, which was only to have the teacher forcing thing like this layer loss. You don't need it after when you want to use the network. So that's why here I have net extract and I only extract the prediction part. Okay. Yeah, this one is basically to reattach the net encoder, and I also add a wait, some surgery. I forgot the detail of everything, but the important point is that you want the net encoder and the net decoder to be back. So it's to say here, input is a string. It means that I have implicitly a net encoder of characters or token attached here, and if I extract only this part, then I will lose it. So I have to reattach it after, and after, yeah, I can predict like I was doing with the previous one. Okay. Okay, we are now coming to the last part of this presentation, which presents an important class of model, which are named sequence-to-sequence or sec-to-sec, and which take an input sequence and generate an output sequence without any constraint, any particular constraint on the length. The output sequence can be shorter or longer. It's not like with CTC that presented Carlo previously. With CTC, we have to produce a shorter sequence, and somehow the alignment between the input and the output sequence has to be monotonous. But here we don't have this constraint. So sec-to-sec are a very important class of model that can tackle a large number of applications, so such as machine translation, where you translate a language to another, or text summarization, when you want to shorten the text and not necessarily linearly scroll through the text to produce the summarization, or conversational modeling, where you want to produce an automated bots. There are also speech-to-text, text-to-speech, a lot of applications. First, I will present the baseline sec-to-sec model before showing an improvement based on sequence attention. So the model was proposed in 2014, and basically there are two parts in the model. The parts that encode the input sequence. So given an input sequence, we are going to produce a fixed size vector that encode all the information of the input sequence. And the second part that will decode, so using this encoded representation of the input sequence, it will feed it to a first state of a recurrent neural network, and then we will generate the output sequence one token at a time. So actually this recurrent neural network here is fed with an embedding of what was previously generated,
And as in the beginning we have nothing, so we feed the decoder first with a special token to tell him, okay, start decoding. And then so using this this representation here of the input sequence, it generates one token. So at the end here is just a classical classifier that decide which output tokens to produce. Then we feed again this previous token to the decoder again and again until it produces a special token to say, okay, stop decoding. So in the Wolfram language, it's done like this. So first, this is the net chain that encodes the input sequence, so with just an embedding layer, a recurrent layer, and we take the last vector on this recurrent layer to produce a fixed size vector here of size 100 that represents the full input sequence. Then the decoder has an embedding layer that takes what was previously encoded, then a recurrent layer, and here we connect the state, the first state of this recurrent layer to the encoded sequence vector, and then a classical classifier to produce the next token. As for the language models that were presented before, we are going to train this using teacher forcing, which means that we feed the input of the decoder with the real targets and not what the model predicted. So yeah, in this part of the decoder, I remind that the decoder has two inputs, the encoded sequence and what it previously decoded. And here we are just going to feed the input of the decoder with the target, using the special start token, and then it will produce, in the same space, the target and a special token to end generating. Okay, so the teacher forcing tree can be done by wrapping the decoder and the encoder into another network, which is similar also to the teacher forcing for language models. The only difference is here we have this encoder part that feeds the decoder part, but after is the same. We have sequence most and sequence rest layer to shift to do the shift of the target, and so the decoder, each sample will be the full target to predict, the full input and target pair to predict. Okay, and so I'm going to illustrate it on the problem of integer addition, but with strings. So we want to pass a string where we depict an addition of integers, and we want the results. And so it's a toy problem. Of course, you can generate as many examples as you want to study this problem. And it's an interesting problem for translation because it's not a linear, a monotonous alignment between the input and the target. Like to this side of this 5, you have to look at this 3 and this 2 here. And then to produce this 8, you have to look at this 5 and this 3. And maybe you have to add 1 depending on the results that you had before. So it's an interesting translation task, I would say, to perform integer addition. Okay, so here I generated some synthetic data set. Here I split into training and validation. So I'm not showing the training. I'm not running the training during this presentation, only showing the results that you can obtain after 1 minute of training on the GPU. It's doing less than a 1% error. So it's working. And now I'm going to show how to use this trained network. There is a little bit of surgery to do. So because if I only extract the network from the results, you see you still have the loss and everything that was added to the teacher forcing. So this we can remove this part using NetState. We take only the encoder and decoder part. Then we take separately the encoder. Okay, it's a net chain, and the decoder, which is this part. Okay, these are the trained ones, and we have to do some surgery also on the decoder to be able to use it. So the first thing is that, the difference between training and decoding is that when training, we were feeding the decoder with the full target to decode. But when we are decoding, we are producing one token at a time. So it's the difference. So we are going to have a procedure where we feed the decoder with one token at a time. And if you use the same net encoder characters as an input to this decoder. The problem is that you will always output 3 tokens when you feed with 1 character. So you could have the input string here and produce the special tokens. Okay, but it won't fit. So instead, we have to change this encoder for NetEncoder class, where each character is a class, and the empty string is also a class that will produce the end of string token. Okay, and so it's working, it's producing, if I put 1 character or 0 character, it's producing 1 token at a time in the decoder. Okay, and the second tricky detail is that this state here has to be removed because we are going to feed it manually using NetState Object. So, okay, so we take the network and we just remove this state. Now we can wrap this decoder into a NetState Object as before, which has, you see, 1 recurrent state here that I can programmatically obtain using net information. So I have the name of this state to be fed manually. Then I can write my function to decode that will just take the input sequence, produce the encoded vectors. Then I wrap the decoder into a NetState object that will keep trace of the intermediate states. I keep in memory all the internal states. I will initialize it with the encoded sequence as the first state. And then before I was using nestlist for language model, here I use fixed point list, which does the same, but which will stop when the results does not change anymore. Because actually when we are going to produce the output token to stop decoding, yeah, we did the strict to map this to the empty string. So when the results does not change, it will means to stop. Okay, and I can decode with this. You see, it's working, it's performing digit an addition of integers based on strings. And I can also compute the outputs on my full validation set and compute the accuracy using classifier measurements. So we have about 90% accuracy, so 10% of errors. So it's different from the error rate we have during training, because during training here, this 1%, it's related to the error rate token by token for each token that you generate. But yeah, actually each output is a sequence of tokens, and so this accuracy here of 90% is at the level of the sequence that you generate, and it's the real accuracy that you are interested in, because as soon as you do 1 error on 1 token, even if your output sequence has 10 tokens, it must be counted as an error. Okay, now I come to an enhancement of the sequence-to-sequence model with attention, which are now the state-of-the-art for machine translation. And so a drawback of the previous approach is that an input sequence is encoded into a fixed size vector, and whatever the input length is, and actually it will always be limited, like you cannot encode a huge sequence into a fixed size vector. And using attention permits to get rid of this limitation. So because we are going to represent a sequence as an encoded sequence with a variable length, we are not going to keep 1 vector only for the sequence. And at the decoding, what happens in attention is that this intermediate representation of what we previously decoded is going to assign weights to all the encoded vectors of the input sequence. So these attention weights are all positive and sum to 1, and we use them to compute a linear combination of the encoded vectors, and it gives a context vector. So it's before we had only one context vector for the full decoding process, and what changed here is that at each step of the decoding, we are going to produce 1 different context vector, which depends on the input sequence and on what we previously decoded, and it's going to change each time. And then we concatenate basically this context vector with the hidden representation of what we previously generated to produce an attention layer. It's more or less similar than the model before, but instead of keeping only 1 vector here, we keep the full encoded sequence, and there is an attention mechanism in the middle. So at each step of the decoding, I remind we assign weights to all these encoded vectors, which produce one context vector here, and we concatenate it with the hidden representation of the decoding, and then, like before, we generate a new token that will be fed into the decoder unless a special token is encountered. Okay, in the notebook, so I don't have time to explain all the details, but I showed you how to generalize and not have a unidirectional but bidirectional MNN here. It's possible. And the decoding part is very similar, but instead of having only one input, so we before we had two ports, what was previously decoded and the context vector. Now we have also a global context vector as before, but also the input sequence that will be fed into attention. So attention takes the input encoded sequence and the output of the recurrent layer in the decoder. Okay, and then we concatenate this and feed this into the classifier for the next token. As before, we train it with teacher forcing, nothing special here. Okay, we train the model. It's a bit longer to train and it's a bit better also. I don't know if you remember, but the error rate was half by 2 here. And we do some surgery as before, extracting first the trained network without the loss, then the encoder, so which has 2 output ports, the decoder. Okay, we change the net decoder and net decoder of the decoder. We also remove this global internal state here, and so now we have this port to initialize using NetState Object. Also here the decoding function is similar as before, and we can apply it and check that it works. And we can compute the validation performance and check that it's a bit better. Yeah, it's a bit better than before. Okay, it's not a big breakthrough, but it was a toy application. But in general, using attention brings a lot of improvement. So it's time to conclude. So to build applications of natural language processing neural networks, there are like 3 or 4 important pieces to achieve. First, the first step is to convert text to a list of tokens or tree of tokens. Today I presented only approaches with list of tokens because the approaches with trees are not state-of-the-art yet. Then we convert all the tokens which are symbols, which can be characters, subwords, words, or multi-words. We convert them to some vectors which are supposed to be semantically meaningful, in the sense that the distance in this semantic space is representative of the semantic distance of 2 words. And then to build the full network, so again, I advise to visit first our model repository, so our model zoo, to see if there are not a network or a piece of network that can be reused for your application. So we have a bunch of pre-trained embeddings, for example. You don't need to train it yourself. You should rather take a pre-trained one. And then the layers for sequences are convolutional layers, recurrent layers, and sequence attention layer. These are the main layers to process sequences that are interesting for text. And then after, once you build your network, of course, you have to feed with your data to be relevant and to optimize. And NetTrain does a really good job with optimization methods that are automatically chosen and are well suited to train on sequences. And so the interesting links are our model zoo. There is also great tutorials on on neural network with a special section on sequence learning and NLP, when you can find many things that I said today. There's also the guide, of course, and there is also this blog here which presents another kind of model, which is the question answering one, where we want, given a text and a question, point a certain the part of text that answers the question. And so if you're interested in knowing how this model works, I encourage you to watch this blog. Okay, thank you very much. Yeah, these word clouds were done using some word embeddings of phrases and distances to the word thank you. Thank you very much for this, for your attention.